Assalamualaikum, sir. So my name is Nur Afifah binti Muhammad SENAWI. We are going to do that part, cryptography and certificates. I'm going to explain for task 1. For question number 1, 1 million RC2 keys every second. So you want to try for 1 million RC2 for every second. So RC2 equal to 40 bits. So the possible key now is 1.1 times 10 power of 12. So we assume that computer can try 1 million RC2 keys every second. So this is the formula for time required equal to total number of possible keys divided by number of keys tried per second. So the time required now is 1.1 times 10 power of 6 seconds. So now we want to convert times to another unit. So from second to minutes, it's going to be 16.667 times 10 power of 3 minutes. And then minutes to hours going to be 277.7823 hours. And then next from hours to days, it's going to be 12 days. It's actually 11.5741 days. But for question number 2, AES cryptographic transformation with 1 to 8 bit. So as usual, we need to find the possible key. So the possible key is 3.403 times of 10 power of 38. The time required now is 3.403 times 10 power of 32 seconds. So from second to minute, going to be 5.6717 times of 10 power of 30 minutes. And then from minute to hours, 9.4528 times 10 power of 28 hours. And then from hours to day is 3.9387 times 10 power of 28 days. And lastly, from days to year is 1.07 times 10 power of 26 years. Next for question number 3. We need to compare the estimate time. So comparing this estimate time required, 1.07 times 10 power of 36 to the age of the universe around 13.5 to 14 billion years, we can see that even with a billion of high-speed computer, it will still take an incredibly long time to perform a brute force attack on a 1 to 8 bit case. Therefore, 1 to 8 bit keys remain highly secure against brute force attack, even with future advance in technology and computational network. Did you have something to add, Tommy?
So we can see that it is obviously that 1 to 8 bit key is more resistant to brute force attack than a 40 bit key because it has more possible values. Okay, you may proceed.
Okay, for question 1.4, the secret is still safe because the higher the bit of processing element, it is more secured. Even with a billion-fold increase in computational power, the time required to brute force a 1 to 8 bit key would still exceed an estimate age of the universe by subatomic margin. So next, for 1.5, here we are assume 2 million keys to try for per second. So the calculation, we need to find the possible key, which is 3.403 times 10 power of 38. And the time required now is 1.7015 times 10 power of 32 seconds. Next, we convert from second to minute. It's going to be 2.836 times 10 power of 30 minutes. And then convert to hours, and then convert to day. The final answer is 1.96 times 10 power of 37 days. So for extra credit question, so the practical reason is why the practical reason is it will provide more security than 1 to 8 bit. Share secret is that they have many more possible value and therefore such more resistant to brute force attack. 192 bit key and has 2 power of 192 or approximately 6.3 times 10 power of 57 different values, while 256 bit keys has 2 power of 256 or approximately 1.2 times 10 power of 77 different value. So in comparison, 1 to 8 bit has 2 power of 1 to 8 approximately 3.4 times 10 power of 58 different value. This means that it will take much longer for an attacker to try all possible keys. However, all else being equal, using a longer key can provide additional security against a brute force attack. So for part 2, I'm going to pass to Tommy.
Okay, thank you to Afifah. Hi, hello, sir. Okay, I'm Tommy. So I will continue with part 2, which is encryption AES 256. Okay, so first we have MOTD.txt with the string university. So I've saved it. And now to command prompt, run as administrator, and I have changed the directory to my desktop. So right now, I will use this command, okay, cert util, which is certificate utility. Okay, so I will run the command. Okay, so you can see it has been successfully encrypted. So it will show a 64 hexadecimal digits. Okay, next I will change for question 2.1. I will change the string to University Technical Malaysia Melaka. Okay, so I save the MOTD text. So back to command prompt, I run the same command. Okay, you can see right now it has been successfully encrypted. Now you see the 64 hexadecimal digits are different. And right now, if I add a new line in the MOTD, I save it, I run the same command. So it generates a different set of 64 hexadecimal digits. Okay, so for question 2.2, right now I will copy this passage. I paste it in the MOTD text file. Okay, as you can see. Okay, it's complete. So I save it. Back to command prompt. After I run, as you can see, it has generated a new set of 64 hexadecimal digits. So for question 2.3, so from my observation, right? So when we compare, all the encryption key are in 64 hexadecimal digits. So no matter what the string value is, whether it's short or whether it's extremely long, in the end, the encryption, right, will still produce output of 64 hexadecimal digits. So this is because it is set to be encrypted for the maximum. And that's all. Thank you, sir.
Thank you.